Now, in this chapter, the last topic is three-hinged stiffening girder. For this three-hinged stiffening girder, you observe this is the girder PQR, or PRQ is the girder where P and Q are the supports, which are simple supports. Now, the cable is ACB is the cable, and D is 10 meters. Central tip is there. Now you should get a doubt. What is this loads that are coming, and I have given a separation. Here you know that your cable is there, and this cable is connected to the deck with the help of suspenders. So here the suspender weights, they will be downward, that is the suspenders will be in tension. So I have just gave a break symbol here. Now in this, now we need to calculate what is the reaction Vp as well as Vq. So note on this. To calculate the reactions of simple supported deck slab at P and Q, to calculate the reactions of simple supported calculate the reactions of simple supported deck slab at P and Q. So Vp plus Vq is equal to the vertical reactions Vp plus Vq is equal to 20 kilonewtons. Now taking moment about P is equal to 0, you can get. So here I am not considering the horizontal reaction, only the free body diagram. Here only it is considered. This is the deck is there. On this deck, this is P and this is Q. A 2-point loads are acting, which is 10 kilonewton. This is 10 kilonewton. And the distance is, this is 20 meters. This is 40 meters. And the overall span is 100 meters. So from this, we got what is the reaction forces in Q and P. Reaction forces Q and P is calculated. Now we need to calculate what is the horizontal thrust. This H value horizontal thrust we can calculate. How to calculate this horizontal thrust? So here understand, we are not bothering about the height of the suspenders. Here we know that at R, at the hinge, that is the moment is equal to 0. So at internal hinge R, write down. At internal hinge R, sigma m about E is about R is equal to 0. So see here, this is the central deck, which is 10 meters. Here a horizontal force is there, and this horizontal force is H. This horizontal force is H. Now here WL by 2. What is the value of W UDL? We don't know that one. Here in the girder, it is given that 2 concentrated loads are acting. That's it. We have to convert these 2 concentrated loads in terms of UDL, that is acting on a suspender. So here, first of all, we need to calculate H value. Just see here, R, I'm not bothering about the length of this suspender. Here at the center of this, take the moments. H into D, which is nothing but clockwise, minus, I am considering the free body diagram, you can take either left side or right side. Take the right side portion, H into D minus VQ. So here minus VQ into 50 meters. From there, we will get, so here a load is, this is VQ, which is 6 kilonewtons. You are taking moment about this point. So H into D minus VQ into L by 2 is equal to 0. So just once again, let me repeat. I am not taking moment about C. I am taking moment about R, where the internal hinge is equal to, that is the moment at the internal hinge is equal to 0. Here, if you consider at this point, just take this, the free body diagram at R, this is R, your VQ force is there. Along with this, where you are considering your, this horizontal force, this is a horizontal force which is acting here. So this will be considered as, don't consider the length of this one, only the dip length will be considered, which is, wait a second, which is acting here. Just your arch is there like this. No need to consider the length of the suspenders. Here H into D. So this point is D. That means how we are considering it, it is similar to our arch problem. It's similar to our arch problem, only here they are cables and suspension bridges are inverse of our arch problem. Something like the load is acting and your arch is there like this. So this is a rise we are considering in the previous arches problem. Whereas just inverse of this is your cable and this cable is considered like this. We are not considering the design of suspenders right now. So this is R and the dip is D. Your vertical reaction is VQ. So VQ into L by 2 and this is H is there. So H is nothing but H into D. H into D is clockwise, VQ into L by 2 is anti-clockwise. So H is equal to 6 into 50 by D is 10, which is 30 kilonewtons. The horizontal thrust in the cable is 30 kilonewtons. Now, we need to calculate here what they are asking, just to see the question. They are asking
maximum tension in the cable.
Okay, the maximum tension is the one. Before that, determine the bending moment and shear force in the gutter at a section 30 meters from each end. So first of all, we will consider 30 meters from P end, that is left end. So right down, consider a section at 30 meters from left end and take left side free body diagram. This is the arch. Sorry, this is the cable. Please note it down. There is a suspension cable, and here this is your point A. Now we are considering that the deck is here, deck portion is here, and in this we are considering at a distance of 30 meters. So this is 30 meters. And we know that at 20 meters, a point load is acting, which is a value of 10 kilonewtons. A 10 kilonewtons point load is acting at a distance of 20 meters. So this is point here, VQ is the force that is acting, sorry, VP, vertical force due to P is acting here. So this value is 14 kilonewtons. Now what they are asking to calculate what is the bending moment as well as what is the shear force. So to calculate that, first of all, we should know what is this ordinate y value is to be obtained. So this is your section XX. So to get y value, we know that this is equation of parabola. So y is equal to 4 into dx by L square into L minus x. Here d is 10 meters, x is equal to 30 meters. So we are considering a section at a distance of 30 meters from left end. So y is equal to 4 into 10 into 30 by 100 square into 100 minus 30. So say what is the value of this y?
Sir,
8.4,
8.4
sir.
4 meters.
So the value of this y is 8.4 meters. Now shear force at XX. So shear force at XX is nothing but, now see this. Your H is there, here it is making, your tension will be like this. It is making a horizontal, this is tension H. Actually your H is there at this point. So this is making an angle like this. So we should know what is the slope. We have to consider the horizontal portion. Let's see this. This is, wait a second. So this is the tension in the one. Here we have to consider at this point the slope of the cable is theta. The slope of the cable is theta, and here it is making horizontal shear in this direction. So shear force is nothing but, the shear is nothing but, here this is H. Just see this one. For the resolution of the forces, this value is H. Now the shear is vertical direction you need to consider. We need to consider the shear force which is resisting in the vertical direction. So shear force at XX is nothing but, now see this, what is the left side upward is positive 14, left side downward is negative minus 10 minus, so this force is there. So your force H is acting in this direction. So just see this once again, I'm just making you clear. See, if you consider here, this is the force H and it is making an angle of theta. Now what is the vertical resolution of the forces? This H will be resolved like this. So if I consider this as something like V dash, just take tan theta. So from tan theta, V dash by H. So what is the value of V dash? H into tan theta. In the yesterday class, I have written the same thing. V dash is equal to H into tan theta, which is coming in the downward direction. So that's why minus H tan theta. What is theta here? Slope of the cable at x is equal to 30 meters. So determine dy by dx according to the equation of this. Dy by dx is equal to 4d by L square into, you can write down this equation as 4d by L square into xl minus x square, which is L minus 2x. Why? Because you are derivating with respect to x. So xl is L minus x square is 2x. So dy by dx at x is equal to 30 meters is equal to 4 into 10 by 100 square into L is 100 minus 2 into 30. You will get in terms of radians, not in degrees.
So 0.16.
0.16 radians. So substitute tan theta in terms of radians only. Convert in terms of radians. So here, this is substitute the values 14 minus 10 minus h is 30 into tan 0.16. So this is in terms of radians. You will get shear force value. What is the value of shear force at xx?
3.91.
3.91 kilonewton. So the shear force, what is the point we represented here? So this is shear force at S. Shear force at S is obtained. So this is nothing but shear force at S. Similarly, bending moment at S is nothing but, coming to the bending moment. Now you are calculating at this section, which is 14 into 30, sagging moment, minus 10 into 10, hogging moment. So this is 10 meters, so which is hogging. And this h is also giving hogging moment only, minus h into y. You need to consider y. So you can remember this simply. This is nothing but positive bending moment or simple supported bending moment minus hogging moment due to horizontal thrust or horizontal force. So this will be 14 into 30 minus 10 into 10 minus h, 30 into 8.4.
68, sir.
68 kilonewton meter. So this is plus 68 kilonewton meter. Now, bending moment and shear force at x is equal to 30 meters from left side is completed. Now, next point is consider a section XX at a distance of 30 meters from right end. So this value is y and this is h. Here this is VQ, which is 6 kilonewtons. There is no other point load acting here. So this is your XX. The distance is 30 meters. So here at x is equal to 30 meters, y is equal to 4dx by L square into L minus x, which is 8.4 meters, as same as the previous one. dy by dx is equal to 4d by L square into L minus 2x, which is also 0.16 radians. Now shear force. So we call it as T, the point T. So shear force at T is equal to Right side upward is negative. Remember, right side upward is negative -6. So here a force of H tan theta is acting in the downward direction plus H tan theta. Only two forces are there. One is H tan theta, which is making a slope here. This is with horizontal. It is making it to H. So the vertical resolution of the force is H tan theta, and this is VQ is over going upward direction -6 plus H tan theta. So -6 plus H is 30 into tan 0.16.
Minus
Just
5.91.
please, let me correct you one point here. Just go back to this point. Here, this is dy by dx is equal to 0.16 radians. This is nothing but dy by dx. We call it as tan theta. We call it as tan theta. Then theta is to be calculated, which is tan inverse of 0.16. dy by dx is called as tan theta. It is not theta. dy by dx is tan theta. Or here you can substitute tan theta is nothing but 0.16. Please make a correction here. dy by dx is called as tan theta. So theta is equal to tan inverse of 0.16. You can get the slope of that one, or directly you substitute tan theta is 0.16. Now this value will be modified. What is this value?
Minus 0.8, sir.
Minus 0.8 kilonewtons. So here also 30 into this value is 0.16. So what is the shear force?
Minus 1.2, sir.
Minus 1.2 kilonewtons. So bending moment at a T is nothing but VQ into 30 minus H into 5. VQ is 6 into 30 minus H is 30 into 8.4 is equal to, what is the value of this?
Minus 72, sir.
Minus 72 kilonewtons meter. So that is negative bending moment. Now in this, what is the last point they're asking? Calculate the maximum tension in the cable. So maximum tension in the cable is nothing but T is equal to square root of VA square plus H square. So here VA is nothing but, don't confuse with VP. So that is VA is nothing but at this point what is the vertical reaction is there, which is nothing but WL by 2 for symmetrical type of suspension bridge. Either it is VA or VB. Now I should get what is the value of this W. I should know what is the value of this W. Can I get this W value in any other ways? Just to see this, if I take moment at C, just listen. To calculate UDLW, to calculate value of UDLW, W acting on cable take moment at C. So this is your cable. The cable is acting like this. So this is having a central dip of D is equal to 10 meters. This is your H. This value is WL by 2. Now take the free body diagram here. This is your point C. Sigma M about C is equal to 0. Minus H into D plus WL by 2 into, so this is UDL, which is acting at a distance of WL by 2 into L by 2. WL by 2 into, wait a second. So this is, you are taking moment about C. So what is the free body diagram? This point will not come. Only this is the part that is coming for the, this is the reaction force is giving positive, it is WL by 2 into L by 2 minus, here this is W. This UDL is W into your entire span, this is L by 2 into, you are considering half of this, L by 4 is equal to 0. So which is nothing but H is equal to, if you simplify, WL square by 8D. From this, W is 8 into D into H by L square. Dip is 10 meters. H is 30 kilonewtons. Length is 100 square. So what is the value of this W? Just let me repeat once again. You can consider this as a horizontal force H is acting. Along with this one here, this is the reaction force is WL by 2. Along with this, a UDL is acting. This UDL value is W. So this UDL W into L by 2 into L by 4 is the moment at C. H into D is the another moment. WL by 2 into L by 2 is another moment. So overall, W is nothing but, what is the value of this W?
0.24.
0.24 kilonewton per meter. So VA is nothing but WL by 2 is equal to 0.24 into 100 by 2.
Sir.
So VA is equal to 12 kilonewtons. Now maximum tension T is nothing but square root of VA square plus H square. Square root of 12 square plus 30 square. That will give you the maximum tension in the cable.
32.31, sir.
32.31. Right. 32.31 kilonewtons, that is the maximum tension in the cable.
Sir, W into L by 2 into L by 4 అని అక్కడ ఎందుకు వచ్చింది ఒకసారి చెప్తారా?
Right, see here. So here how many loads are acting on the cable? This is A, H is the horizontal force, WL by 2 is the reaction that is acting. Your cable is there like this, right? So this cable is actually loaded with a UDL of intensity W per meter length. So the span is L. If the span is L, then what happened here? This value will be WL by 2 for symmetricity, WL by 2. This is W. Now horizontal force is there, this is H, this is also H. Now when you are considering the moment about the center of the cable and the dip is 8 meters or 10 meters, you have to consider a section here and take either left side or right side. So I take left side one. So this UDL intensity is also to be considered. The call was disconnected. ఎక్కడుందా మీరు నేను చెప్తున్నప్పుడు మొత్తం అయ్యిందని చెప్పినప్పుడు
No, sir.
No, it was disconnected.
Sir.
Okay, now see this. This is the cable. This cable, it is having a reactions H as well as VA. So when you take the free body diagram, this is the free body diagram. This is your H, this is your VA, and this is loading W. So this is nothing but H into D, anti-clockwise, so minus H into D, plus VA into L by 2, the distance is L by 2, so VA into L by 2. UDL is there, so W into L by 2 is the load, multiplied with the moment, L by 4. So something like WL square by 2, you can simply say it as WL square by 2. Of a suspension bridge cable of span 80 meters and central dip 8 meters is suspended from the same level at 2 towers. The bridge cable is stiffened by a 3-hinged stiffening girder which carries A single concentrated load of 10 kilonewtons at a point 20 meters from one end. Calculate the shear force and bending moment at 30 meters from each end. So this is the question. So it is similar to our three-hinged arches only. Three-hinged suspension bridges are as similar as that of three-hinged circular arches, but in case of three-hinged circular arches, here the cable is subjected to only tension, whereas given arch, it is like this. This is subjected to radial shear, bending moment, and shear force. In case of this, the deck is being subjected to shear force and bending moment. As it is linear, there is no radial shear. That's it. That is the difference what you have to observe. And the concept is slightly same. Now, in this case, what we have to calculate is, first of all, we need to calculate what is the vertical reactions of. So this is your horizontal force. This is WL by 2, point A. WL by 2. This is H. Now the suspenders are available. Which is W per meter length. So why I am giving this break is nothing but these are vertical suspenders. They are connected to the deck as well as they are connecting the deck or the girder as well as the cable. So these now they are in tension like this. This is something like whatever the notations you give. So this is the three hinges are available, and my center of this dip is nothing but C. So this point is C. Now the central dip is mentioned in the problem as 8 meters. So this is 8 meters. Now something like I call it as P, Q, R. Here vertical force is there, which is V suffix P, V suffix Q. And it is mentioned that a point load is acting. And the value of this point load is 10 kilonewtons, which is acting at 20 meters from. So here a point load is there. So just make a point load which is of 10 kilonewtons. at a distance of 20 meters. So this is 40 meters. Entire span is 80 meters. Now VA, that is, first of all, you take VP plus VQ is equal to 10. You consider this portion only right now. This medium only, VP plus VQ is equal to 10. Then minus VQ, if you take sigma M about P is equal to 0, VQ into 80 plus 10 into 20 is equal to 0. VQ is 2.5 kilonewtons and VP is nothing but 10 minus 2.5, 7.5 kilonewtons. So VA, VP and VQ are calculated. Now considering the at internal hinge R, at internal hinge R, sigma M about R is equal to 0. So that implies you consider the free body diagram either left side or right side. VQ into L by 2 minus H into D is equal to 0. So this is nothing but 2.5 into 80 by 2. 2.5 into 80 by 2, span is 80 by 2, by D is 8 meters. Is it right? H is 12.5 kilonewtons.
Yes, sir.
So the H value is calculated. Here itself you can calculate what is the value of this W. So taking moment about A, this sigma M about C is equal to 0. H into minus H into D plus W L by 2 into L by 2 minus W L square by 8 is equal to 0. That is W L by 2 into L by 4, W L square by 8, which is nothing but H is equal to W L square by 8D. And here we want W value H into 8 into D by L square. 8 into D by L square. So H is 12.5 into 8 into 8 by 80 square.
Point 125, sir.
0.125 kilonewton per meter. So that is W. So now what they are asking here, they are asking to calculate the shear force and bending moment at 30 meters from each end. Consider a section XX at the rate of 30 meters from left end. 30 meters from left end. So draw the free body diagram for this. This force is VP and at 20 meters you are having a point load of 10 kilonewtons. So this is VP. What is the value of VP?
1.5, sir.
7.5. So Vp is 7.5 kilonewtons, which is a distance of 20 meters here, and this is 30 meters. And here you need to get what is the h is there, and this y value ordinate is to be calculated. This is the cable. For this cable, y is to be calculated. So to get that, first of all, y is nothing but 4d into x by L square into L minus x. 4d, d is nothing but 8 meters by 80. 80 square into 80. 30 into 80 minus 30.
7.5 meters.
How much?
7.5.
7.5 meters. So dy by dx is equal to 4 d by L square into L minus 2x. So 4 into 8 by 80 square into 80 minus 2 into x is 30. So dy by dx, what is the value of this dy by dx?
0.1, sir.
0.1.
Yes, sir.
Now, shear force at x6 is equal to, we are calculating at 30 meters, so left side upward is positive plus 7.5 minus 10. So shear force at x-axis is plus 7.5, which is going in the upward direction. Minus 10 is coming in the downward direction. Then here we already observed minus h tan theta. This is minus h tan theta. So 7.5 minus 10 minus h value. So h value is calculated, which is 12.5. So 12.5 into tan theta. Tan theta is 0.1.
So minus 3.75.
Minus 3.75 kilonewtons. So this is shear force at x is equal to 30 meters. Bending moment at xx. 7.5 into 30 minus 10 into 10. So you are taking moment about this point. That's it. Draw the free body diagram and consider the moments. Minus h into y. So for the simplicity, you can consider this is simple supported bending moment and minus h into y. So here this is 7.5 into 30 minus 10 into 10 minus h. H value is 12.5 into y 7.5.
$31.25.
So positive 31.25 kilonewton meter, that is the bending moment. So we are being asked to calculate what is the shear force as well as what is the bending moment. That's it. So now the next part is they are asked to calculate from the right hand. So consider a section XX at a distance of 30 meters from right hand. So this is y is 7.5 meters, that is not changed. L is also here 30, x is 30 meters. Now there is no other loading except these points. Actually, here we need not consider this point. Why? Because we are not considering this. So here this is the one. We are calculating for the gutter. Consider a section 30 meters iterations of XX iterations of 30 meters from right end. So from the right end means here this is your VQ, which is a value of 2.5 kilonewtons. So shear force at XX is nothing but VQ minus H tan theta. VQ value is 2.5 minus 12.5 into tan theta. So tan theta is nothing but 0.1, which is as same as the above problem, which is 1.25 kilonewton. The shear force is
Sir, right side upwards.
right side. Yeah. This is minus 2.5 minus VQ plus H tan theta. So minus 2.5 plus 12.5. Is it okay?
Yes, sir.
So you will get it as minus 1.25 kilonewtons. Minus 1.25 kilonewtons. Now bending moment at XX. Bending moment at XX is VQ into 30 minus H into 1. VQ is 2.5 into 30 minus 12.5 into 7.5.
Minus 18.75.
Minus 18.75 kilonewton meter. So this, now we require maximum tension in the cable. Your VA will be WL by 2. You already got W value 0.125. So 0.125 into 18 by 2.
Newton, sir.
How much?
5, sir.
So VA is 5 kilonewtons. Maximum tension in the cable T max is equal to square root of VA square plus H square. Square root of 25 plus 12 point, which is 5 square plus 12.5 square. What is the value?
13.46.
sir.
So this is how we will calculate the 3 hinge suspension bridges. Okay. So now we have to move to the next chapter. Till now we completed cables and suspension bridges. The cables and suspension bridges we completed regarding the concepts of suspension bridges, components of suspension bridges. Then we have seen that if there are series of point loads are acting, then what is the shape of this? The shape of the cable is funicular polygon shape. And then afterwards, when a UDL is acting, upon UDL acting, it will be considered as a parabola. The profile of the cable is parabola, and the length of the cable is L plus 8 by 3 into d square by L. So that is the length of the cable which is to be considered for a suspension bridge. So we have seen that the supporting systems at the ends will be there. These two supporting systems will be two types. One is the rope or the tension cable which is passed through a frictionless pulley. And the second condition is when it is passed through a saddle, where the supporting system is saddled. Then how to calculate the tension forces, and as well as how to calculate the forces coming on the tower, supporting tower, that we can calculate. And the last concept is three-hinged suspension bridges. This three-hinged suspension bridge is a stiffened case where the statically determined structure is considered, and we can calculate what is the shear force and bending moment at any section, considering the free body diagrams.